Hi everyone, we're going to look at radical equations today, mostly square root equations, although we will look at a couple with cube roots in them. So let's start with an example. 3 minus the square root of 2x minus 9 equals 1. Now in general, when we're solving equations, our goal is to isolate the variable, and that's no different here. But we're going to start by isolating the radical, and then we can isolate the variable by squaring both sides. So in other words, I'm going to start here by subtracting the 3 from both sides of the equation, which means that I now have negative square root of 2x minus 9 equals negative 2. Now I don't need to get rid of the negative on both sides. I can square it either way, but I do want to think about the fact that this is the same thing as 2x minus 9 equals positive 2. So in either case, I square both sides, and I get 2x minus 9 equals 4, which when I then go about solving it, 2x equals 13. X equals 13 over 2. Now, that is the answer, but with radical equations, and I'll explain why with our next example, with radical equations, it's really important that we verify. And we verify back in the original equation. So 3 minus the square root of 2 times 13 over 2, which is just 13, minus 9, which just gives me 4. So in other words, 3 minus the square root of 4, which is 3 minus 2, which is 1, which is what I was after. So this does work. Now, I know that you've been told your whole lives that you should check answers. This is going to be a case where you absolutely must. And we're going to look at the next example and see what happens if we don't. So 5 plus the square root of x minus 1 equals 0. Now, if I go about the exact same thing I was doing in the previous example, in other words, I subtract 5 from both sides, I get the square root of x minus 1 equals negative 5. Now, something might already jump out to you, and you might be screaming, I already know what's going on. That's fine, cool. We'll come back to this step right here. But let's say nothing like that does jump out at you. Also totally fine. If I go about now squaring both sides of the equation, I get x minus 1, and negative 5 squared is 25. Add 1 to both sides, we get x equals 26. So there's a solution. But if I verify this solution back in the original equation, 5 plus the square root of 26 minus 1 is 5 plus the square root of 25, which is 5 plus 5, which is 10, not 0. So this answer actually doesn't work in my original equation. This is what we call an extraneous root. It's an answer we get when we've made no mistakes in our algebra whatsoever, but it isn't a solution to the equation. In fact, this equation has no solution. Let's talk about why that is. And we'll do it two different ways. One, we're going to go back to this step where I commented that there might be something hinky going on here. So square root of x minus 1 equals negative 5 is problematic because we have such a thing as the principal square root. This right here is the principal root, which is a fancy way of saying it is the positive root. So in other words, the square root of x minus 1 has to be greater than or equal to 0. But negative 5 is not greater than or equal to 0. So it doesn't matter what I plug in there. It's never going to give me negative 5, which means I could have known right from that step that there was no solution. Now, if you're solving an equation like this and you notice something like that pop up, it won't always be quite that obvious. But if you notice something like that pop up and you say, oh, well, this has to be positive, it can't equal negative 5, no solution, you can stop right there. You don't have to keep doing algebra at it. You can say, all right, I know that this is the principal square root, can't equal negative 5, therefore no solution. So that's that's the reason why this occurs. Graphically, I can also illustrate what's going on by thinking about this function as y equals 5 plus square root of x minus 1. So y equals 5 plus the square root of x minus 1 is half a parabola, like this. So this is y equals 5 plus square root of x minus 1. When will that equal 0? When will y equal 0? Well, it never will, because there is no x-intercept. So y has to be greater than or equal to 5 in this case. So there's no x-intercept, therefore no solution. But why do I get a solution popping up in my algebra? Well, the reason I get that is because I squared both sides of the equation. And when I squared both sides of the equation, I completed this parabola. I drew the second half of this parabola. which is the function y equals 5 minus the root of x minus 1. In other words, my actual equation is calling for the principal root, but there is also a negative root, and that negative root will cross when x equals 26. So if I were solving the equation 5 minus the square root of x minus 1 equals 0, then I would do all the same steps I did above. I would move the 5 over, negative 5. I square both sides. I get x minus 1 equals 25, because when I square the negative and I square the positive, I get the exact same thing. In both cases, I get x minus 1 equals 25, x equals 26. It's just, if I was dealing with negative root, that would not be extraneous. That would actually be a solution. But because I'm dealing with the principal root, it isn't a solution. So the upshot of all this is, anytime you square an equation, you have introduced some ambiguity. You've introduced the possibility that it could find the answer for the wrong root. That's why you always have to verify your answer back in the original equation. So moving on to a cubed root, let's say I have the equation 5 minus the cubed root of 2, and then in brackets x plus 11, all equals 7. The extraneous root thing doesn't occur with cube roots, because cube roots don't have a principal root and a negative root. Cube roots have whichever sign they have. So I go about it the same way, though. I'm going to go ahead and isolate the radical part of this. So I get the negative cubed root of 2 times x plus 11 equals 7 minus 5, so 2. When I cube both sides now, I'm cubing a negative, so I'm going to get a negative. So negative 2 times x plus 11 equals 8. I can choose to go a couple different ways here. I'm going to divide by negative 2, but I could just distribute the negative 2 through those brackets. But I'm going to turn this into x plus 11 equals negative 4, which means x equals negative 15. You don't really have to check cube roots because extraneous roots don't happen, but it's not bad practice. So if I say 5 minus the cubed root of 2 times negative 15 plus 11, well, negative 15 plus 11 is negative 4, which means this is 5 minus the cubed root of negative 8. So in other words, 5 plus 2, which is 7. So that is a correct answer. All right, I'm going to now write down 4 examples for you. And what I'm going to recommend is that you pause this video and try these 4 examples. Try to solve these 4 equations before coming back and seeing the answers. So we have 2 plus the square root of x plus 3 equals 7. We have the square root of 2x equals x minus 12. It's a little more complicated than anything we've done so far. We have 3 times the cubed root of 5 minus x plus 1 equals 7. And we have 2x plus the square root of x minus 1 equals x plus 7. So go ahead and pause the video here and try those equations. But I'm going to go ahead and I'm assuming you've now gone off and practiced them. So here are the solutions. We have the square root of x plus 3 equaling 5. So we square both sides of that. And that one's pretty straightforward. We get x plus 3 equals 25, which means x equals 22. We go through and check. So 2 plus the square root of 22 plus 3, which is 25. So 2 plus the square root of 25 is 2 plus 5, which is 7. That is correct. That's what we wanted. So this is a correct answer. X equals 22. In example 2, you may have struggled a little with this, and there's a really common mistake that happens, so I'll walk you through that. But the radical is already isolated here, so I actually don't need to do any manipulation before I square it. But what I do have to keep in mind is that when I am squaring both sides of the equation, I am squaring the entire side, not just the pieces of the side. So when I square this, I get 2x on the left. On the right-hand side, I get x squared minus 24x plus 144. Now, if you just put x squared plus 144, that's a really common mistake, but it's one you can't continue to make. I'm squaring a binomial, so there's distribution involved. In other words, this is x minus 12 times x minus 12. This is now a quadratic equation, So I'm going to move everything over to one side of the equation, x squared minus 26x plus 144. You can just use the quadratic formula at this stage because these are kind of biggish numbers, but it is factorable. It's x minus 8 times x minus 18, which means I get two solutions here, either x equals 8 or x equals 18, and I have to check both of them. Sometimes they will both work out, sometimes neither of them will work out. In this case, we'll just assume I'm checking it on my graphing calculator, so just plugging stuff in. In this case, the 8 does not work. And you see it if you check it by hand, that on the left-hand side you get the square root of 2 times 8, so the square root of 16 is 4, which is positive. But on the other side you get 8 minus 12, which is negative 4, so that doesn't work out. But the 18 does work, so we have one solution, x equals 18. For the cubed root function, I have 3 times the cubed root of 5 minus x equals 6. I don't have to divide by the 3. I'm going to, because then I work with smaller numbers and it's a little bit nicer, and 6 is divisible by 3. If it wasn't and it would introduce fractions, I probably wouldn't bother. But 6 divides nicely by 3, so there we go. Now when I cube this, I get 5 minus x equals 8, which means negative x equals 3 or x equals negative 3. Cube root functions or cube root equations, you don't have to worry as much about checking because the extraneous root situation doesn't exist. We don't have a principal root and a negative root, we just have one root. But good practice to check anyway, so I would plug these into the graphing calculator. Just a side note to kind of show you what would have happened if I had not divided by the 3. When I cube both sides, I have to remember to cube the 3 as well. So that becomes 27 times 5 minus x equals 216. So bigger numbers, but when I divide this out, 216 divided by 27 is 8. So we end up in the exact same place we ended up before. But bigger numbers, so not always the nicest. And remember that in your IB exams next year, you will have a paper with no calculator. So it's good to have practices that have you working with smaller numbers. Question number 4, we're back to a square root. So we're going to isolate the radical, which means I have the square root of x minus 1 equals negative x plus 7. Again, I have a binomial. I don't just have a number. So when I square both sides of the equation, I have to remember that I'm squaring that whole binomial, which involves distribution. So I have x minus 1 equals x squared minus 14x plus 49. Move everything over. I get 0 equals x squared minus 15x plus 50. This one hopefully is a little more obvious what the factors are. X minus 5, x minus 10. Again, you do get two answers and you do have to check both of them because sometimes one will work, sometimes both will work, sometimes neither will work. In this case, the 5 does work when you plug it back into the original equation and the 10 does not. So we have x equals 5 as our only solution. So hopefully you tried those, and if you got them wrong, you know what you did wrong so that you can avoid it next time. We're going to do one more example together. And this is an example in which we have two radicals. So if I have the example, the square root of x minus 3 minus 2 times the square root of x plus 5 equals negative 5. Now the fact that it's equal to negative 5 is actually not a problem because we have 2 and I'm subtracting, so negative numbers are potentially going to exist. But if I just square both sides of the equation, because I have to distribute everything, I don't get rid of the square roots. So I can't really isolate the radicals to start, but what I'm going to do is I'm going to isolate one of them. It doesn't matter which one. In this case, I'm going to isolate the x minus 3 root because that's going to give me then a positive 2. Root x plus 5 minus 5. Now that I've isolated one of them, I'm going to square. This isn't going to be enough in and of itself. So when I square the square root of x minus 3, I get x minus 3. When I square the other one, I have to distribute, which means I'm going to end up with 4 times x plus 5 minus 20 times the square root of x plus 5 plus 25. So just to kind of quickly walk you through where that comes from, it is 2 times the square root of x plus 5 minus 5 times 2 root x plus 5 minus 5 remembering that we've now got 4 multiplications in here. So 2 root x plus 5 multiplied by 2 root x plus 5 is where my 4 times x plus 5 comes from. And negative 5 times negative 5 is where my plus 25 comes from. The minus 20 root x plus 5 comes from minus 10 root x plus 5 minus 10 root x plus 5. Now, this doesn't really seem better, but it is because now I only have 1 square root. So I'm going to go ahead and isolate that square root now. So distributing out that first binomial and then moving all the non-root parts over to the other side, I get negative 3x. Minus 3 minus 20 is minus 23, minus 25, I get minus 48, equals negative 20 root x plus 5. And now when I square both sides, here's where my numbers are going to get kind of gross. And in this case, I'm not going to bother multiplying by or dividing by the negative 20 because it's going to give me fractions and I don't really want fractions. But when I square that binomial on this side, I get 9x squared. My middle term is going to end up being minus plus 288x. And then 48 squared is 2304. On the other side, I do have to remember to square the 20, so I get 400 times x plus 5. Quadratic again, so I'm going to bring everything over to the same side. 9x squared minus 112x plus 304 equals 0. I'm definitely not going to bother trying to factor this one. I'm just going to go to the quadratic formula. It does end up being factorable, but I'm not going to waste my time trying to figure it out. So I get x equals 112 plus or minus the square root of. Now, when I figure out the discriminant, negative 112 squared minus 4 times 9 times 304, I get 1600. That's how I know it was factorable, because 1600 is a perfect square. So because 1600 is a perfect square, it was factorable, but not really worth wasting my time for. So this is 112 plus or minus 40 over 18. If I subtract the 40, 112 minus 40 divided by 18, I get 4. And if I add it, 112 plus 40 divided by 18 simplifies to 76 over 9. I do have to verify these. This is an example where I would definitely just use my calculator to verify. And I have to verify them all the way back in the original equation. So I'm verifying them back in the starting equation, root x minus 3 minus 2 root x plus 5. And I'm checking that I get negative 5 when I sub it in. That's where a calculator is very handy here. They do both work. So in this case, I have 2 solutions. And I should represent them as a set. So 4 or 76/9 are my 2 solutions. So that's a lot of work to do it, but the process is basically you isolate your radical, you square or cube both sides of the equation, and then you solve from there, either by isolating the variable or solving a quadratic by factoring your quadratic formula. If you have 2 radicals, and we're not going to give you 2 radicals if it's not a square root. We'll only give you 2 radicals if it's a square root. But if you have 2, you isolate one of them, square it, isolate the other one, and then square it again. So you're going to have to do 2 steps. If I had 3 radicals, it would get nightmarish, but the process is kind of the same. It just involves more and more and more steps. And you can find practice for this in your Pre-Calculus 11 book. Oops, I can spell. Pre-Calculus 11, and it is section 5.3.